What's in your head? How would I know? I'm a physicist. My goodness, my Guinness, how would I know? I know what's in my head. My head is full of bubbles. And they haunt me, and they chase after me all the time as I eat them, and I drink them, and I breathe them, and I think them. But let me try to be a bit more poetic. Your man D.H. Lawrence wrote many books. One is called Women in Love. And what does he have to say? But the pressure was too great. He would have to find something to make good the equilibrium. Something must come with him into the hollow void of death in his soul, fill it up, and so equalize the pressure within to the pressure without. For day by day, he felt more and more like a bubble. Well, when I woke up this morning, I cleaned my throat. Excuse me. I washed myself. I shaved. I shaved. And you have to give this talk a couple of times to figure out putting that one. I went downstairs. I made myself a nice cappuccino. I went to work. I just had a very light lunch. I had a roll. And something sweet afterwards. I ate a mousse. Then was the afternoon, and that was a bit hard to get through. And all day I was looking forward to a nice pint of this in the evening. And your day was probably quite similar. You're surrounded by foam wherever you go. That foam won't be very far from you, and even now, you sit on a piece of foam. It could be the cushion, or it's just your bum. Your bones, some of them are of a foam structure, of a cellular structure. So, foams are everywhere, so what are they? Foams are collections of gas bubbles, normally surrounded by liquid. But that liquid, which in this case is a beer, or here it's washing up liquid, doesn't always have to be liquid. It can also be solidified. And if it's solidified, what do you get? You get a roll. How do you make a roll? Well, you have a dough. You mix in milk and sugar and the likes, and you might put in a bit of baking powder, and then you put all that stuff in the oven, and you bake it up, and if it's hot enough, the baking powder is going to release the gas, and then this stuff you take out again, and it settles, and it solidifies again, and you have a solid foam. Now bread, and I'm going to pass this sample around. I'm going to pass around another sample as well, which looks very similar. And that's that sample here. This is foam made from aluminium. And let me put this on the overhead here. So just that you can see that cellular structure. Okay. One can foam up aluminium as well. One grinds normal aluminium into powder. One then adds something to it which releases gas, like a baking powder. That's what people used initially. Then you put it in the oven. You heat the oven up so that the aluminium melts. And at the time when the aluminium melts, the gas needs to be released from the baking powder. And then you have to quickly take it out of the oven because it won't be stable very long. And then the aluminium just freezes again, solidifies again, and you have this type of material. So let me pass around 2 aluminium samples here, and please bring them back. I know some of you are hungry. If you're hungry, it's a bread roll. I don't need that anymore. So this is also a project that we are involved in on understanding the structure of these type of materials. Why would you want to have an aluminium foam? People use that as a building material for parts in a car. Namely, it can absorb an awful lot of energy because most of it is air. It's empty. So the impact will be you feel the impact in the foam and not in the driver. So there are quite a number of different car companies now that use these materials, these foams, for the crash zones. And we are involved there in a project which is interestingly funded by the Space Agency, European Space Agency, because we also send some of our samples up into space to study how they evolve when one can switch off gravity. So that's one of the projects that we're doing. Now, as you can see, with something like that, foams are generally a disordered mess, and therefore it's hard to study these things. If you have a crystalline material, you have a periodic unit cell that keeps on repeating. In this case, that's not that doesn't repeat itself. So one way of studying of studying foams is to go into 2 dimensions. And you can do this. Here I have a jar full of liquid, water, and very liquid foams very well. So I've used this, and now I make a foam just by shaking this. I mix in the gas. Okay, so I come back to this experiment. That's an experiment. I come back to that later on. I take out some of that foam. Spit is a bit in the way. But it's, of course, another type of foam. And I take some of that foam, put it there. Could have been too much. And I need my second gas plate. Okay, and now I have a foam which is 2-dimensional, and this is easier to visualize and easier to theorize about. Now, if you look at that for a while, and I leave this there, various processes are going on there, but at the moment I'm interested in the structures. I want to squeeze out a bit of that liquid here, and I can break that overhead projector because it's not mine. And so if you look closer, and I invite you afterwards to come here because I have a couple of demonstration experiments here. If you look closer, then you see these lines, and 3 of these lines always meet in one point, and they are curved lines. And all the lines are arcs of circles. And you never have more than 3 lines meeting in a point. These are equilibrium rules that work for the 2-dimensional foam, and essentially come from the fact that the surface or the line energy of this foam will be minimized. Now, the driving factor for all foam structures is the minimization of surface energy. And here I have a little toy tool. I can make a film, an individual soap film. Can anybody see anything in the first row anyway? You see the film? Yeah. Now you grab that bit. No, the bit in the middle. Slowly. And look more, and you let go. Oh, now try it again. You grab that and let go. So there is a little soap film in the center in that square, which just burst. And surface tension pulls this back. So you want to give that a go. And there we go. Okay. And that means, because it pulls it back, because the area, this area is larger than that area. So this is an example where I can see the minimization of the surface tension. And then, similar to this, where I have three lines meeting in a point, I can take these kind of frames and dip them into surf solution, and then I get very regular structures. Again, I need to look at that. And maybe you can tell me how many lines do you see meeting in a point?
3, 4.
4 lines meeting in a point. Correct, because we have one dimension higher, and this is another example of such a structure. And they also meet on the very well-defined angles. In the 2-dimensional case, they meet on the 120 degrees. In 3 dimensions, they meet on the 109 degrees. And so foam, the structure of foam is determined by the minimization of surface energy. We can go to 2 dimensions to make it easier to realize that. If we want to understand the structure of 3 dimensions, then what we normally do is we use computer simulations. And that brings me on to another little story that I would like to tell you. Well, at the same time, I should maybe ask you to just have a closer look at the structure as it evolves in time. And the thing is also evolves in time. There you notice that the liquid is draining out of the foam with time because of gravity. So I can shake this up again. It's all white, and then the liquid drains out. But you will also notice that with time, the bubbles will go bigger and bigger because the air is diffusing and that structure is coarsening. And this is my link to one of the talks, this cellular structure does not look too different from the large-scale structure of the universe that we heard before. And that was the first presentation I ever gave in Belfast when my supervisor Dennis sent me there. Could have been the end of my career, but we managed to get a paper published in the Irish Astronomical Journal, which no longer exists today. Okay, now I've mentioned Dennis Weir, so let me tell you a little story there. So we do lots of computer simulations, and one story relates to the structure of foam in 3 dimensions. And this goes back a long time, 120 years, when the idea was, if all the bubbles have the same volume, what structure would fill the whole space and would minimize the surface area? In 2 dimensions, it would be a honeycomb structure. But in 3 dimensions, the structure would be different. And the famous physicist, Irish physicist Lord Kelvin, came up with that problem, and for the reason, and that brings me to the second talk, that he was looking for a structure of the ether, the structure that carries the electromagnetic waves. People thought there's a medium, and he thought, well, it could be a foam. At some stage, he thought it was a drop of tar. And again, there's no more ether nowadays. So he dreamed up a structure, worked it through, and this is a cell. I can take this as one bubble, and I could put all these bubbles together, and I can fill space, and I always have 4 lines meeting in a vertex, and I have the right angles. And he worked this out. There's a subtle curvature in it. It's quite a hard piece of mathematics, but he did it all. So for 100 years or so, people thought this is the ideal foam. Well, there weren't that many people thinking about it. But anyway, for 100 years, this was the best thing that you could do. Until Dennis Weir came along, and he had a very bright student at the time, Weaire-Phelan, and they came across a nice piece of software that allowed to simulate these structures with a computer. And Dennis had some ideas of what to try, a trial structure, and I put it in a computer, and I found, oops, it's better than the Kelvin structure by 0.3%. It's better. And it looks more complicated. That's why I needed a computer. This is a unit cell. These are 8 bubbles. And if I take this unit cell and have a copy of it, I can paste it into the various directions, and I can fill the whole space with it. All the bubbles in there have the same volume, but they're two different types. It's a more complicated structure. But so there is no mathematical proof that this is the best structure, and there probably will never be. It took mathematicians 350 years to prove that the honeycomb structure is the most optimal structure in 2D. It's a very hard problem to prove. But people think it is the best. Now that's part one of that story. Part two is that you can't predict what's happening. This was back in 1994, and about 10 years later, Dennis was contacted by Arab company, design engineering company, who were looking for a building for the Beijing Olympics. They were looking for a building for an aquatic stadium where your man, what's his name, got Michael Phelps got 8 gold medals, better than Mark Spitz, which I should remember. And so they wanted to have a special design, and they came up with the water cube. And this is the identical Weaire-Phelan structure. They used exactly that structure. They used the same software to make this. It has the advantage, because it's repeating, they only had to build a certain number of pieces. It's like Lego blocks. So I pass this around. And I also have the original t-shirt. Sent from China. So that's the water cube t-shirt. So then the situation back to 2012 was that the structure existed in a computer. It existed in real life, but only in China, and it was very big. But nobody ever managed to see it in an experiment. While there are ways of making this Kelvin structure very easily. It's very tricky for this, for the Weaire-Phelan structure. Until we had a great visitor over to my group who had an idea how to do this, and we used a 3D printer. We made a special box into which we made grooves, so individual bubbles could fit into the groove if they were the right size. We knew how to make them the right size, and we were able to fill up that box with bubbles, with 2,000 or so bubbles made with fairy liquid. And we looked at it and thought, yeah, that's it. That's the baby. That's the Weaire-Phelan. And so it took a photograph. So this is a photograph of the Weaire-Phelan structure made with fairy liquid bubbles. The bubbles, each bubble in diameter is about 0.6 or 0.8 of a millimeter. So they're quite small, but it's very visible. And if you want to try to see that, you can compare it with that structure. If you know what you're looking for, it's easy to see, else it's a bit tricky. So now you can make that particular structure in the lab. So at that stage, I have no idea how I'm doing with time. I want to go back to a few of the other foam properties that I mentioned before. Well, I actually only figured out at the beginning today that I was supposed to speak about light. I heard light, there was light entertainment, so I didn't know. So let me talk about light then. Okay. A foam is made of liquid and contains gas. Right. What colors does the gas have? That's these were, yeah. No color really. What color does the liquid have?
Everything but black.
And the foam is made of black and no color, and it's white. Why is that? Interesting enough, the first person who asked that question, I was where does the color of why is a foam always white? Was Robert Boyle, another Irish physicist, in 1660. He wrote about the color, the whiteness of a foam, and he explained that light is scattered by the individual bubbles in the foam, and therefore you can't see through it, and the backscattered light then appears white in your eyes. Now, if you have an individual bubble, you notice there's the colors of the rainbow that you see in a bubble, as you see in oil drops and so on. Because you have many bubbles, all these different colored light that comes back to your eye will mix again, and you get white light. While the blackness here is the absorption of light. So this is the blackness of this very iconic symbol, really, of Ireland, anyway. And to come back now to the first talk, because I mentioned soap, the first talk was about nanoscience. Now, if I manage to get this thing out and make a bubble, the PhD from physics and chemistry. All right, there you go. But I would consider myself more a theoretician. There we go. Well, you get the idea. It's not very good. It's true. I got it as a child. Anyway, the thickness of a soap film can be as thin as a few nanometers. So here you got a nano-sized object, namely the thickness of a soap film. That's the nano thing. Sometimes when I think now nano is something completely new, but everybody who blew a soap bubble created something nano. It's extended, but in one dimension it is nano. Especially that big, if you observe a bubble for a long time, it turns black. You get little black dots called Newton spots, and they are the nano-sized bits. That's what the film is the thinnest. So, where was I? Talking about light. So I've covered that, the whiteness. This again is an image which now is dried out, and you can see, if I focus it a bit better, the bubbles have gotten certainly bigger than they were before. You see these curvatures now better. You really see now these three lines meeting in a point, and so on. Okay. The other thing that I had in my hand was this stuff. Okay. A foam made of bubbles and of liquid, but this here, I need something to. If you give me a beer mat. Give me a beer mat. Okay. Is this a liquid or is that a solid? This looks like a solid to me. But when I squeezed it out, it was a liquid. Now it's a solid, but I can move it. And I can make it flow again. And then it's a liquid again. And you know that type of behavior, which is related to physical-rheology, also from non-drip paint. That is liquid when you shear it. And if you don't shear it, if the force isn't big enough, it's a solid again. So there's a whole field of people trying to work out how does that work in detail as the individual bubbles move past each other. So this is another aspect. I mean, lots of simulations with regards to that. I've mentioned that we get some funding for ESA to do this work on these solid forms. We now get also funding from Science Foundation Ireland for a process whereby paper is made with the suspension of the wood fibers not into liquid but into foams, and it helps one to create more uniform paper structures in that process, and also to foam up and make paper material from fibers that normally one couldn't use for that. So let me then go back to the beginning. So what is in your head? So let's see again whether that stuff makes sense. So let's see stuff again. Lots of bubbles. I did a rough calculation today that the bubbles in Guinness are about 0.1 of a millimeter in diameter. I think you could squeeze about 1 million in there. But maybe I made a mistake. But something like that, 100,000 I would say, you get into a pint, because they're really, of Guinness, because they're really small. So lots of small bubbles. And the foam needs to be stabilized by something. Obviously you don't want fairy liquid in there. something that lowers surface tension and brings some dynamic surface tension effect to it, stabilize it. Is in this case of beer, it's proteins that stabilize that, which come from malt. The gas that's used in beer generally is CO2, except for Guinness. One uses CO2 plus a lot of, tries to use lots of nitrogen bubbles. I come back to that in a moment. This gas is, if you have beer in a can, it's dissolved in there, and if you open the can, then you release the pressure, and the gas that's been pumped into the liquid will be released. So it's a super saturated liquid. What do we want as a consumer from a pint? Well, obviously it should taste nice, but we also want a good head, because that indicates that it's fresh. You also want to, when you drink it, you want to have some lacing, that the glass is covered, tells you how many sips you had, or whether somebody else drank while you went to the bathroom. So this is another effect. It depends on the glass shape and so on and so like. So that's the standard pint of lager maybe. But for Guinness, there are a few other effects, and one you've already mentioned. So Guinness is made with nitrogen, and nitrogen is not very soluble in liquid. Only a factor of 1/60 as soluble as CO2. So it's hard to get the nitrogen into the Guinness. So the guys from Guinness had an idea to make these cans, and I prepared that one earlier. Mm-hmm. So you know these type of cans that you open up and lots of head comes out, and it looks like a pint has been poured from a tap. And that contains this floating widget, which is a little ball. And when the beer is put into the can, so this is a ball that's empty, but gas is pumped. This liquid in the beer is going to be pressurized, and nitrogen is being put in there, and also some liquid nitrogen, actually, and the gas doesn't then have to go into the liquid, but it can go into this hollow. So this is filled with the gas. Now, if you then open, and it was pressurized, now if you open the can, and you normally don't open it like that, then the gas will be released from that floating widget, and it will stream up and will stream out, and by doing that, it will create lots of small bubbles. So this is invention number one, and I read up that the patents that Guinness got that actually dates back to the 1960s. So this is number two observation of Guinness. The first thing was the colour. I forgot anything. The second observation, and this is something you read about it in the newspaper every other year, the bubbles. Oh, they go down really, don't they? Why do they go down? And can they go down? I mean, have you ever had a pint, let's face it, have you ever had a pint of Guinness where the bubbles were at the bottom and the black stuff was on top? No. Doesn't happen. Maybe in space, I don't know. But anyway, so obviously they go down along the side, but what goes down goes up again. They have to come up again, and they go up through the center again. So there is a convective motion that takes place, and this, I suppose, is helped by the fact that the bubbles are very small, and the forces that you need to push them in this convective flow is reduced. Maybe if they're too big, they're just too buoyant if you have CO2 bubbles. So that's the main thing. The details of these effects are always very, very tricky. But we have done such, we can see such convective motion in the lab quite easily. And then I also wrote the final thing there. There's the Guinness Cinder, whatever it's called. You can place a pint of Guinness from the extra stout on some machine, and it foams it up very quickly because it's being subject to ultrasound radiation, and that releases the bubbles. So then, to finally summarize everything, I need what do I need? I need the other page of my script. Where is the other page? The other page is here, and I need something else. There might be somebody who holds a microphone.
Yes.
Thank you. So let me summarize. Why should you care? They're full of air, and not very long they will last. When you were young, you chased one by one a colourful blast from the past. I find their maps so appealing. You say you just like their feeling. I'm forever blowing bubbles, pretty bubbles in the air. They fly so high, nearly reach the sky. Then like my dreams, they fade and die. Fortune's always hiding. I've looked everywhere. I'm forever blowing bubbles, pretty bubbles in the air, pretty bubbles in the air.
Thank you so much, Stefan. That was absolutely fascinating and really nice to have a theoretical physicist in the mix of experimental physicists that we've had here this evening. So, are there questions from the audience based on all of those talks and all of those props that we have? So, we'll take the first one from Arlene.
Stefan, I'm quite keen to learn, where did your love of, obviously you've acknowledged bubbles every single day, everywhere, and all of the objects and things you use and eat, etc. Where did your fascination come from in relation to bubbles?
I think, sorry, I can just manage to destroy my shaving foam. No, I think what I always like is well, it's pretty, I find it aesthetic, these structures, and I also like the disordered stuff. Because normally in college you talk about order structures, crystalline structures, and you look at that and you think it's all messy until you look closer and you find out the various correlations in that stuff. So it's visual, it's something where we can do the simulations and the experiments at the same time. It's where you can do easy experiments, hands-on stuff. That's what I like, and it's nice maths as well. So
Super. We need to hear more about the mathematics of it as well. We have a question here.
Yep. Hi, Stefan. You mentioned something about the point of Guinness having, I think you said skimmings or markings on the point of Guinness glass, so you know whether somebody has stolen your drink when you come back from the toilet or whatever it was. But it was just when you said that, I noticed that yours had none. And this is anecdotal, not scientific, so don't lynch me. But anecdotally, if you leave a pint of Guinness for an extended period of time, you won't find any markings.
correct.
Right, so
I was dying for that pint all the time, but I knew I'd be on. So it was there for about half an hour. And I think that justifies just what you said.
So the question, that if I could just ask the question, the question was that, sort of from a working class, the conventional wisdom is that you don't take more than 20 minutes to drink a pint of Guinness, otherwise it goes to shite. And also, you shouldn't drink it out of those new age glasses that you're staring upstairs.
Okay, so for the people down the back, I'm not sure if you heard the question summarised very succinctly at the end is, should you just drink your Guinness in 20 minutes because otherwise bubbles are all going to go from the side of the glass? And are the new age glasses kind of crap?
It happens very rarely that I take more than 20 minutes. What happens if that, I'm not going to be able to answer the question, but what happens is that the foam will dry out, more liquid goes down, and maybe that's why it just sticks to it in a different way. The bubbles will be slightly bigger because there is diffusion in there. I don't know what the answer is, but I certainly, the fact that you said that looks like a stale pint, it was a stale pint, so I mean, it proves you're right.
And the new glass.
The glasses, I don't know. Is this thing inside as well?
See, I don't think it is actually.
I mean, people do all sorts of things with glasses. I know Carlsberg a while ago, I think they roughened up the glasses inside, a very fine with lasers, so that the sides of the glass act as nucleation sites, and the bubbles can form there. I don't know whether they do that with Guinness. Stick to the glasses you have. I don't think it needs to change. Right? I'm from Germany, so for every type of beer we normally have a different kind of glass, yeah, and you get used to that. And if somebody gives you the beer in the wrong glass, you're like, oh, what's that? Yeah, so the shape will make a difference, but the details are tricky.
You're a connoisseur, so I would stick with your intuition on that one. Is there another question for Stefan? Yes?
Not a question, but I'm told that the best way to drink a pint of Guinness is 2 half pints, 2 separate glasses, because the time it takes you to drink it is deteriorated.
It's more expensive.
I was told about, this was about my first week in Ireland. When you're a guy, never order a glass. So I haven't done it.
But you pay so much for 2 half glasses that the Irishman said, I'll put up with the pint.
Maybe we should get the barman in this conversation eventually as well. I have a question, because you mentioned that, and you have the fairy liquid here, and that's used for all of the props that you have tonight. What actually makes the fairy liquid better than the others, or is that just good marketing?
It's not just good marketing. We use different stuff, but if we buy some very cheap washing up liquid, it just doesn't foam very well. We just use it, it's stable. I don't know what's in it. My chemist colleagues hate us for that because we use fairy liquid. But we say, well, who cares about chemist? No, we don't say that. But we just want a stable foam. So one thing that I wanted to get across in this talk is, to some, at one glance, the fairy liquid foam is the same as the Guinness foam, it's the same as the shaving foam, it's the same as the spit. They have different bottle sizes, but the foam is the same. Only then, once you've done and explored that, the chemistry comes into role. But the first thing is physics, and one can get a lot out of that just saying it has a surface tension, whatever it is, I don't care.
Well, I think that's a really nice way to end it. The first thing is the physics. Please give another round of applause for Stefan.